Okay, hi everyone. So today I'm going to talk about my thesis, which is about real-time state estimation for contact manipulation. I'm Peter Yu. I'm a PhD student working with Alberto Rodriguez and in the M-Cube lab. M-Cube stands for Manipulation Mechanism at MIT, and we focus on the robotic manipulation part. So the main theme of this thesis is about localizing an object in real time in the manipulation scenario, like pushing an object from A to B. And we want to make it more robust and accurate by fusing touch and vision. And we also want to incorporate a history of observations so that it can be robust to occlusions or sensor noises. There are some noise. Okay, so why do we need state estimation? So nowadays, most industrial robots are used in the car manufacturing type of process, which is they pre-program with a fixed path to do welding, gluing, or painting. So those robots can move very fast and accurate. But in contrast, let's take a look at what we are trying to get the robots to do in the past 3 years. Like in the past 3 years, we joined the Amazon Robotics Challenge, and the task was to pick up object from the shelf or pick up object from a cluttered tote, and the objects never seen before are like a novel object. So what we are seeing here is okay. So what we are seeing here is lots of variations, just like the tasks in these two cases. So we want to picking up objects, but we don't exactly know where it is. So pre-programmed fixed path won't work. Or we want to inserting object after we picking up from a shelf into a populated box to pack it tightly. So those we need more smart sense of the environment. So the key questions here is we want the robot to be able to answer where's the object and sometimes what's the object. And challenges here involves occlusions in the task, such as the object is behind the other, or more often is the robot itself, its gripper is getting in the way of the camera, so it will get occluded. And there are some sensor noise both from the cameras and tactile sensors. And we also want accuracy. So normal in manipulation task, we would like to have the accuracy at the millimeter level. And the speed, we want it to be similar to the human performance so that it can really benefit human. So approaches here are first, as I said before, is we want to fuse touch and vision. And in this thesis, we are focusing on how to use touch, and that's the main contribution. And we want to optimize over a history of observations so that the process is more robust. So here's today's outline. There are 3 projects that I will talk about. The first one is shape and pose recovery in the tactile exploration process. It is pure touch only and using batch optimization. And the second project is pose estimation in planar pushing. Here we are adding the vision input, and we want the estimation to be in real time. And next, we will do pose and contact state estimation in the insertion task. So here we move from 2D to the 3D task and also deal with complex contact situation. So now let's get into the first project. So at the very beginning of my PhDs, we are thinking of what is the most difficult task and state estimation task in manipulation. And I was inspired by this picture where a human can easily figure out what's inside the bag just by touching inside it. And we can find out what's the common objects and know where it is and pick it up. So we wonder how can a robot have the same capability? And especially we are focusing on the on the problem of finding the object shape just by touching. So here a caveat is that touching will move the object because it's an intrusive sensing. So since it will move the object, so that means probably not only the shape, but also the pose estimation is important so that we can aggregate all the contact points together. So if you think this is a chicken and egg problem, so it's very interestingly similar to the SLAM problem. SLAM is a classical robotics problem, which stands for simultaneous localization and mapping. So it was dealing with like having a mobile robot into a new room, how to build a map of the room and also localize itself. So compared with the SLAM problem, which is mapping the environment, here we are mapping the shape of the object. And in SLAM, we are localizing the mobile robot itself, and here we are localizing the object. And there's a key difference is that in SLAM, we will have the odometry to predict where's the object motion, what's the object motion. In the object, we usually don't have odometry, but instead we have like a pushing mechanics, some physics to predict where the object is going. So here are some related works that's doing tactile sensing on objects. So there are shape estimation, pose estimation, or shape and pose estimation. So they all assume some knowledge of the shape or have some constraints on the pose. Okay, so for example, Straub in 2014, this is most similar to our work, but it is constraining the object to pin down the rotational axis. So what we want to do is, given a movable rigid object on the table like this, and we want to find its 2D shape just by touching with a single finger. So the problem inputs are the contact points and contact normals during the exploration process. And the problem outputs are the shape and poses of the object during this manipulation. So at the beginning of this study, we try to collect data and write a simulator that try to explore this block by contour following. So this block is following some physics rule to move around, and during the exploration, we record the contact points and contact normals. So after 4 rounds of exploring this object, we got this messy data like the left-hand side, lots of contact points and lots of contact normals. And what we want to do is to output the poses of the object during this exploration and also the shape of the object. So here we note that for each time step, the measurement is pretty little, like we only have 1 contact point and 1 contact normals, but we also, during the process, move the objects at every time step. So we want to exploit as much as possible the information that we collected. So our approach is using least squares optimization. It can be seen as the graph SLAM in the SLAM community. So in the optimization, we describe the shape and poses as follows. The shape is the control points along the boundary of this object. And the poses are just x, y, theta of the center of mass of the object. And we want these variables to satisfy several constraints via cost functions. So the first one, shape prior cost, is like we know this object may be looking like a circle, so we impose that kind of cost. And measurement cost is like if there's a contact point happening there, it should be right on the object. And the motion cost is similar to the odometry in the SLAM scenario, and I want to talk about more in the next slide. So what the motion cost is about is like we want to know, given this push, how will this object move according to physics? So we want to penalize what the physics-based motion model the difference between the physics-based motion model and the estimated poses. And the motion model that we are using is by Lynch, proposed in 1992. It's about, there are several assumptions here. First is quasi-static pushing. That means we are pushing it slowly, and that's more or less match the exploration speed. And secondly is we assume we know the surface pressure distribution between the object and the surface. And the third one is we use a limit surface approximation. And limit surface is a representation to help us to map friction force to instantaneous velocity of a 2D object. And that helps to predict this motion quickly. All right, so now let's come back to the optimization problem. So after we define all these three costs, we sum all of them together and assign a proper weights of them to propose an objective function. So now I jump directly to the result. So we try on various shapes, and those are initialized as a circle, but after the exploration and optimization, we are able to get the shape and poses of the object. So here, the solid line represents the estimation of the shape and pose, and the dashed line are the ground truth of shape and pose. And here, we are pretty excited and published this work in the IROS 2015, and titled with Shape and Pose Recovery from Planar Pushing. So after this, we try to work on the real experiment. So we find that this work does well in the simulated data, but not well in the real experiment. So what we found is that the real pushing has a lot of uncertainty from frictional interaction, like between the object and the surface, and also between the pusher finger and the object. And as you can see, the real data looks much messy than the simulated data. So at this point of the research, I try to redefine our goal. Like first, because we hit some hard challenges, like the pushing motion is one, and the tactile information is actually pretty sparse when you are trying to reconstruct the shape of the object. And the tactile exploration also takes time and space because, it takes time and space, and it's usually not suitable for industrial usage. So we are thinking about what is in a practical scenario. And at that time, we participated also in the Amazon Picking Challenge, which is about picking objects from shelf. And it is okay to add some visual measurement as an initial guess of where's the object. And also, it's okay to use the camera to find out what's the ID of the object and look up a table to find out the shape of the object. But the harder challenge is we need a real-time performance so that during the manipulation, like picking up the object, we want to adjust for the errors. So although we are redefining our goal, but we are reusing some of the technology we developed before, such as the pushing mechanics. So here we come up with this new task, which is doing pose estimation in planar pushing. And here we add the vision as the extra input, and also we try to make the estimation in real time. So before diving into the detail, I want to compare what can we gain from visual and tactile sensing. So we want to promote that we want to use vision for the rough estimation and then use touch to refine in the last inch. So from vision, we can see visual sensor can provide very good, rich global information. But when occlusion exists, the vision is of little use. In addition, intrinsic and extrinsic calibration errors also make the information not accurate. And on the other hand, Tactile sensors provide only local information, but they can be very close to the object, and the measurement is accurate with respect to the robot finger. So vision and tactile information complement each other pretty well, so we would like to find an efficient way to combine them. So here I will use a pusher slider system to describe our approach. So first, we want to create a real-time estimator to accept the following inputs. The first one is a visual pose detection. We use a webcam looking at the camera, and there's an April tag to help the vision process. And the reason to do so is that we want to get realistic noise from the camera, but we also don't want to work too hard on the vision problem itself. So, and we collect contact information from the pusher by having two force torque sensors at the base of the fingers. And we have the pusher motion from the robot. This is an industrial robot, so it has pretty accurate encoder values. And the output are the poses of the object in real time, so x, y, theta of the object. One thing to note that from the input, we expect the camera can give us roughly like 1 centimeter accuracy. And from the pusher, from the contact information, we are expecting like millimeter accuracy. So fusing them, we hope that can get better estimation. So the key challenges here includes that there may be missing inputs. If the camera cannot look at it, there are occlusion happening, then we don't have camera measurements. And if the pusher is not touching the objects, then there is no tactile sensing. And vision sometimes will give outliers when like lots of noise happening. And our approach is using ISAM. So ISAM stands for incremental smoothing and mapping. So it's coming from the SLAM community. But we can look at it at the core, it is a online nonlinear least square solver. So online means that during testing time, we can add variables and constraints, and it will give out the answer pretty quickly. So the variables here are the object pose at every time step, and the visual measurement cost. That means we want the estimate to be close to what camera says. And there's contact measurement cost, saying when there's contact happening, the pusher should be just right in contact with the object, not contacting remotely or have penetration. And there are motion costs that's saying we want the object to move according to some physics law. And you can see that here the bottom two are just the same as in the first project. And here we assume Gaussian noise models, so it is a very common way to speed up the inference process. So let's take a look at the problem in the factor graph way. So at the middle of the graph is the post variables of every time step. And on the top is the visual measurement, okay? And then there's the factor or the constraints that's constraining the object to follow the visual measurement. And on the bottom is the tactile measurements that enforce the contact constraint and also the motion model constraint. So the whole optimization is just the sum of all these cost functions, and we will use the ISAM to solve the whole problem. So let me highlight some experimental results. First one, we want to say that contact helps to keep track of the object under occlusions. So at the beginning of this video, we can see that the camera can see the object, see this view ray, and our estimate is marked with a red color. So next, I'll play the video and notice that there are occlusions happening when the robot is trying to manipulate the object. And at this point, I pause it, and now I continue, and you'll see that the red or estimate using the vision and contact, it can still keep track of the object. But the cyan one, which is the place last seen by the camera, still at this place. Okay, and then the second result is that we showed contact can improve accuracy. So let me play this video. So at this point, I pause and let's look at it closer. So we can see, so now I'm plotting the ground truth in black and vision input in cyan, and the vision and our estimate in red. And notice that with a pure visual estimate, there's a penetration here that was corrected properly by fusing the contact information. Okay, and then the third result is that we show it can handle multiple kinds of objects. We try this kind of object like a butterfly, and this elliptic shape, and a rectangle. And this work was published in the ICRA 2018. The title is Real-Time State Estimation with Tactile and Visual Sensing, and with the application to planar manipulation. All right, so now we are moving into the third project. So we are going into the post and contact state estimation in the insertion task. So we are moving from a 2D post estimation to 3D, and we are also dealing with complex contact states. So this insertion process is actually also inspired by Amazon picking challenge, where after picking up the object, we want to pack it tightly so that we can save space and also save cost. So here we are focusing on the mating process, which is getting this object from the suction cup and trying to put it into this gap, this hole in the box. So here the idea is that first, from the force sensing at the wrist, we put a force torque sensor at the wrist, and this is the suction cup. And normally we will see that the visual estimate will have some offset from the ground truth. And we hope that with the force sensing, we can detect there's a contact happening. And we also want to know from the force sensing, like what type of contact is that. So with that knowledge, plus the geometry of the object and also the boxes, we want to refine this estimation. And the second idea is that we want to use the robot kinematics. The robot can tell us if it's moving to the right, then the object should be also moving to the right. And we want to use it to remove some errors, such as like outlining, visual detection, or there are sometimes occlusion from the camera, and also there's visual delay when because the normal camera spit out the data at the 30 Hertz normally, and the robot can read the encoder value at the 250 Hertz. So here is our insertion estimation setup. So we can see the inputs are the visual post detection and the force measurement at the wrist. Here it's a force torque sensor that measures six numbers. And the robot motion from the encoders, which can be very accurate. And the outputs are the 3D pose of the object. And there's two extra things, which is the contact formations and contact points. I'll talk about more in the next few slides. Next, we have the Vicon system here to monitor where's the object to provide a good ground truth. And that's good for data labeling and calculate the noise parameters. And then challenges here is that the contact formations between this rectangular object and this hole is rather complex. And from the force reading, we cannot distinguish that very easily by just looking at the reading. All right, so let's talk about the contact formations. I'll use a cuboid object to describe it. So for this, contact formations roughly describe how does the object contacting its environment. So here is an example of contact formation 1, which is this corner of the object contacting the right wall. So if we look at from the object bottom view, it is correspond to this point, and this is edge contact between the object and the wall. So you can see that if we talk about it, there's a contact formation 2 that we define, which is edge contact along the length of this object. So this line corresponds to this line from the object bottom view. Okay, so why do we need these contact formations? So first, practically, it's a very good information to find out how to adjust when there's contact happen. And secondly, because the optimization we are using, it expects smooth cost functions. Smooth means that's differentiable. So if we can know these contact formations beforehand, we can ensure that cost functions to be smooth. So next, how do we recognize these contact formations? So to resolve it, we use a pretty simple scheme because we want real-time estimation. So we feed the force measurement, which is 6 numbers, feed it using a SVM, train a SVM to predict the contact formation ID directly. And we totally have 8 contact formations here. So during online testing, then after we predict this contact formation, then we can add the contact constraints accordingly. So if it's formation 1, then we add these constraints, like saying that they should be put together. And here is a technique to make the accuracy higher. That is, we use a self-supervised data labeling. So remember we have this Vicon system to track the object very accurately. So we can use that to calculate the contact formations. So it can help us to collect like thousands of data and achieve more than 80% of accuracy. So after we are done with the contact formations, then we can plug in our old ISAM framework. So the variables here are the 3D pose of the object and also contact points. So the contact points are, we enumerate all the contact points that could happen on the wall of the object and also on the bottom of this object. And we impose, first we need to impose, like these contact points should be on the right geometry feature. So if it's on the object, so it should be constrained on the bottom of the object. So next is the contact measurement cost. It's trying to enforce the contact constraint. So after the formation is known, then we say they should be meet together. And there's motion cost that's from the robot encoders to say that if the robot moves to the right, then the object should move accordingly. And there's visual measurement cost that should say our measurement should be close to the visual estimate. So now I'm giving you a feel of what the real testing data looks like. So at the left-hand side is the real data images. On the right, I'm plotting the visual input in green and also the ground truth in gray. So you will see a tiny error here between them, and that's the error that we want to deal with adding the tactile sensing. So first, I would like to say about the contact formation accuracy. So So on the left-hand side, I use the rectangular object and I plot the confusion matrix. So you will see most of the time works well, and there are some errors happening in the close by formations. That's usually okay because they are just pretty close by, and also we incorporate a history of the measurement, so those kind of error can be filtered out. And on the right-hand side, we also try on the ellipse object. So it only has two kind of contact formations. One is contact to the right, one is to the left. And that is mainly because it's a smooth shape, so we don't need like 8 contact formations. So with less contact formations, we can achieve a much better accuracy. And the second result is we want to see how the contact point estimation works. So before a contact is made, like here, so there's virtual contact points around at the bottom of the object and also on the wall. So let me play this video. So when the contact happens, like there's contact constraint happening, then the contact points will join together, and that's the place where the contact point happen. So, okay. And the next result I want to show you is the contact really improves the accuracy. So on the left-hand side is without the contact constraints, and on the right is with contact constraints. So here, red is the estimate, and gray is the ground truth. So let me pause at the middle of a run. So they are from the same data stream, and we can see that the one with contact constraint, the estimate does not match the ground truth well. And on the right, we see with the contact constraint, the estimate is closer to the ground truth. Because when the object is making contact with this wall, then it can correct for the error. And also, even when the contact is broken, because we have the robot motion constraint, so it can still keep that correction. So the fourth result is we wanted to adapt our system to a new object. So especially the ellipse bottom, which has a more smooth curve. So we, because of our system is described with modules, so it is easy to swap the components. There are two changes involved. So one is we need to define a new set of contact formations, and we also need to collect the new data and train the SVM. But we have this automatic labeling system, so this process will not be hard. And there's contact point costs that we need to adjust, saying like the contact point is on the bottom of this object. So these are not hard, but need to be careful. And finally, we have a state estimation and estimation system, and we want to see how can this help in the real insertion process. So at the beginning of the process, the object is localized by the April tags. And later, you'll see at the initial alignment, there's a misalignment there. And what we are doing is a very simple control policy. Like given a contact formation, we map it directly to a correction reaction. Okay, so you may notice that there's a speed up here, and that is right now mainly bounded by the communication with the robot, and that can be improved by advanced protocols. And this project is submitted to IROS 2018. The title is Real-Time State Estimation with Tactile and Visual Sensing for Inserting a Suction-Held Object. So we are done with these 3 projects. We went from touch-only batch optimization to touch plus vision and work in real time. And then later we move it to 3D pose. and also complex context states. So in summary, this thesis proposed an real-time state estimation framework for contact manipulation, and we fuses touch and vision and incorporates a history of measurements so that we are more robust to some failures such as the occlusion to the camera. And the results shows that the tactile sensing improves the accuracy, and it can work in real time at around 100 Hertz. And it can be adapted to different shapes of objects. And we show this system using the two iconic manipulation tasks. One is the pushing task, and the other is the insertion task. So for future work, we would like to integrate our state estimation with some reactive controllers or planners. So here are two ideas inspired by my colleagues. This first one is the hybrid model predictive control for pushing. So in this task, we want the robot to push an object from A to B and be robust to some disturbance and uncertainty of friction. So in this task, the state estimation is pretty important here. So on the other hand is the prehensile pushing. In this task, we want the robot be able to plan a trajectory and reorient the parts in hand. So in this task, if we can enable the state estimation in hand with tactile sensing, then we can better monitor for error and plan for reactions. So with this slide, I want to mention something that I didn't talk about in this presentation. So we talked about three things here, but there's a pretty important work that I collect a large-scale experimental data set for understanding pushing. So in the real-world pushing, we know there's lots of uncertainty happening, but we want to quantify how much uncertainty is that. And that it was published in IROS 2016 with a title called More Than a Million Ways to be Pushed. And it was nominated for a Best Paper award. And on the other hand, there's a separate thread that's running in parallel. That is, we participated in the Amazon Robotics Challenge for the last 3 years. In the first year, I tried to build up the software framework. In the second year, we work on the multi-view object pose estimation. And that's using camera only, and that's complementary to my thesis work. And the third one is we show that in last year, we are able to pick up novel objects. Novel means things that's never seen before by the robot. And we directly predict the affordance of the objects. So what's next? So the next step, I would like to keep on pushing the robotics manipulation. Keep on pushing, yeah. Keep on pushing this manipulation technology so that we can really deploy the technology into customers so that it can really benefit the general public. So I want to thank all of you for joining this thesis defense. So especially I want to thank my thesis committee, Alberto, John, and Thomas, Justin. So thank you for your support and giving me very great insight to my thesis. And especially I want to thank Alberto for providing this wonderful experience working in the M-Cube lab. So, and I want to thank the M-Cube lab members for making the lab look like a family, like home. So it's very good for working together. And I want to thank my first year colleagues and the DRC team for making me up to speed when I first joined MIT. And I want to thank my family, especially my wife, Yifei, who take care of the family, myself, and our daughter, Shushu. And I want to thank all the other mentors and friends for making my PhD journey wonderful. Thank you. And with that, I'll conclude my talk here, and I will welcome some feedback and questions. Thanks. Yes.
So, as I understand it, you're still doing the least squares ISAM.
Yes.
So you're using a separate pre-filtering thing to decide which instances of time you add the contact constraint.
Yes.
And that keeps rolling, that stays fixed. So once at time t, I added that constraint, I keep moving. That will always be on at time t. Is that right?
Yes. Yes.
Which is somehow, I don't know, that feels more scary to me in the contact case than in the sort of slab case.
Yeah.
Do you find that problematic?
So, yeah, sometimes because that's kind of rely on the contact formation recognition.
Right.
So, yeah, you're right. So that's what we are working on to try to push the accuracy of the contact formation. And so far, we are looking at is fine if the accuracy is high enough and make sure it doesn't have prediction that's far away from the current estimation. And since we also incorporate a long history, so it can easily filter out the noisy predictions.
I would be afraid it wouldn't. I would be afraid that you're putting in some weird hard constraint that, back at time t minus 15 says I was in contact, and it's a stiff thing that it might corrupt.
Yeah.
But you think it does filter out nicely over time?
Yeah. It is a worry that I have, but so far, on the most cases, it works fine there. Yeah. Thanks. Yeah, see. Yes. Yeah. So in that case, so after we know the poses of the object relative to the wall pretty well, then we can just have a simple way of calculating all the corners, bottom corners of the object, and see where it falls inside no, it's just the Vicon cameras looking at the pose. And yeah, we can know where's the corner exactly relative to the wall. So with that simple technique, we can find out what's the contact formation. And we also use just a four-stroke sensor to see whether it's making contact or not. Yes.
In your second project, you shared results of vision-only tracking of objects while pushing.
Yeah.
And also touching vision.
Yeah.
Do you have any results of just using touch?
Just using touch. Yes, we had some sort of ablation test, and the result is that we cannot keep on blindly predict that for a very long trajectory. So that's why we add this vision. So roughly pushing for 10 centimeter, that's okay to predict it. But after that, we probably want the robot to move away, maybe look at it again. That's the whole scheme. Yeah. Yes. Yeah. Yeah, so in that collection, we didn't intend to insert that object. So we're just exploring around the whole of the object. Exploration strategy is, so we have roughly probably 2 centimeter in translation error and a 15 degree. And we try to just move down until contact, and we just enumerate in that range. Yes.
So in the last experiment, I saw you with SVM and the post-hoc sensing information
So you say there are multiple formations that's not inside the 8 formations, or?
I mean, there could be case that it's just impossible to distinguish between two contact formation, right? For example, you could have 2-point contact. For successor, it will feel the same as 3-point contact.
Oh yeah. So here we the contact formations, it probably doesn't enumerate all kinds of formations, but we try to find out what's the major ones. And the contact points here we means the two end of the edge contact. And it's possible to have just 1-point contact there, but it's not the major type of contact that we will encounter. So there's a policy when selecting the contact formations. We try to eliminate some that's minor contact, and we want to keep the set small so that the accuracy can be high enough. Yeah.
So did you have any experiments where we always talk about contact can cause sort of divergent trajectories.
Mm-hmm.
Did any of your testing sort of put it in a regime where, like, for instance, a glancing collision that might have happened or might not have happened, and if it did happen, the object would rotate, even quasi-statically, but if it didn't happen, it would just keep going straight.
Mm-hmm.
I mean, those are the cases, I think, where the turning that constraint on and sticking with it might really get you. Did you see anything like that? Did you test those kind of situations?
Yeah, that's the problem that we often worry. I feel the closest scenario is when you're pushing a block at maybe at the corner. So that's where it may happen. And so far we don't try to use that kind of cases. And in the pushing task, at the beginning we use one point pusher, and that's very, very unstable. And that's why we add 2 pushing. So I would say that's an interesting thing to explore, but realistically, we want the state estimation to be good enough.
Can I
yes.
ask that? It might be related to Russ's question.
Yeah.
So, like, in state estimation, say for vehicles that would have 0 velocity update, say wheel and rotor nodes, vehicle stationary, and that can be very powerful in reducing the uncertainty. But if applied incorrectly, it could cause things to go wrong. So, what would be worse, applying a contact constraint when you're not in contact, or being in contact and not appropriately estimating that you're in contact?
Yeah, I think it's the situation where there's no contact, but you detect there's a contact. Because usually contact constraint is pretty hard, like it will just snap to your object. So we usually tend to make it more conservative, saying like putting the threshold to be lower so that you really have to make a very good enough contact, so then we detect it's a contact.
We can talk more in the closed. Are we going to have a closed question session?
Yeah, I think we will.
You have the CISA advisor. I really love your graphics and visuals, but I would have expected more sort of like time series plots of the estimated mode of contact versus the actual, if that's accessible, and also the uncertain bounds and how they behave.
Yeah.
Do you have anything, like the backup slides or anything, or just to describe to us how do these experiments sort of unfold in time, and do the covariances that you estimate behave well? And did you do any like consistency checking in the sense of how your estimate of the uncertainty compares with, say, an independent estimate of the uncertainty from the black line?
So in this thesis, in this presentation, I didn't include that, but on the thesis, we will have that kind of plot. But I can show you some result first on the, we are always talking about like fusing a long-term trajectory. And here is what we are looking at. We can't try to compare with EKF. EKF is usually have one-step estimate. And we can see from EKF with 1 step and ISAM with 200 step. On the translation side, there's slight improvement, but there's a big improvement on the rotation side, and that's really helpful because like ISAM keeps all the observation and it can do the relinearization to make the estimation more accurate.
Suppose you had you left the robot running overnight. Maybe you did this, but you had move an object to the left, move an object to the right, just run it forever.
Yeah.
Would it stay nice, or would it eventually get unhappy diverge?
So you say with one finger pushing?
Yeah, say one finger push to the left, one push
Yeah,
to the right.
yeah.
And just for a very long time, would it sort of be well behaved, or would it somehow like some instability, some area would get unhappy?
So we did that several times. Like if we don't have any kind of feedback, then we just push with one finger. It's very likely that it will just turn, and you cannot just go there and push it back. And yeah, there are some colleagues that does the control, like adding the control to make sure it's staying on the right path.
So maybe just to clarify the question, I think
Yeah.
what John was asking if whether the state estimator would remain stable, independently of what the object does. Like, would the state estimator have drift or
diverge and without looking at it?
Well, even fusing the vision and the touch. Imagine if you had 2 fingers in a square.
Yeah.
And you're just going back and forth.
I think with vision it should be pretty okay because every time you can relocalize it, and that's why we want to add this vision. Like imagine the car going through a tunnel, and after going out, it sees the GPS and it can know where it is exactly. Not exactly, probably roughly where it is.
But I think the point of the question is,
Yeah.
how does it handle outliers, right? So
Outliers.
So, you know, what's the likelihood that you put in a constraint that would be wrong and mess up the estimation? I think that was what they were getting at.
Okay, so you're talking about the outliers.
Well, imagine the problem is things go wrong. And
Yeah.
so is there some, like, the sensor, the fingertip touches the tabletop before it hits the object, or something happens to violate some of the assumptions that, like, it's easy to, I'm not saying your videos are wonderful, and I'm not saying it's not a lot of hard work behind it. It's easy to get a video of it kind of working well once, twice, 10 times. But in terms of like deploying a robot in some house.
Also the real answer, not the PR answer.
Yeah. Yeah, so
Only the other students should be exposed to this kind of thinking.
yeah, we are kind of cutting the beautiful videos out of the experiments, and I would really say, like the normal case in the pushing side, like if we're really pushing for a long trajectory but without having vision, then it definitely will diverge a lot, and then usually it's just robot moving out and vision look at it, and we can start again pretty nicely. Yes, Jaji.
So often we would use certain motions, or often in the form of multiple constraints, so we can reduce the uncertainty to a lower dimensional space. How does ISAM or this formulation take that into account?
So I don't perfectly understand the question. So
it seems motion is a cost.
yes.
Observation is a cost, but quite often you can apply an action, and the result of that action, you definitely know that there's one-dimensional uncertainty is gone.
Yeah. Yeah.
Something,
Yeah. Yeah.
there's a table there, so the z-axis, the z-value can never change.
Mm-hmm.
So how could those be incorporated in the formulation?
Yeah. So I think that's roughly similar to when the insertion task, when it touched the wall and it reduced the z uncertainty. So I would say like we propose this framework, and it's easy to add your own cost function if you have extra knowledge of something. So yeah, I would say that it's easy to add some new constraints if you know any new information.
Okay, so it looks like should clap. Maybe we should invite the audience to step out and we have internal discussion.
Thank you. Thank you. Thank you. See you. Thank you.
竟然能听懂一些。
Thank you. Thank you. 好，拜拜。
杜博不是杜博，我讲 Peter
梯子。
鱼啦鱼，每次都 KT。